Almost every image or molecule generator starts by deciding how big its output will be, and then paints into that fixed frame. But what if the size of the thing you're creating should itself be decided as you go? This paper builds generative models whose canvas can grow during generation. Let's build the idea from scratch: the intuition, the real maths, and then the actual algorithm. Here's the constraint baked into today's models. A diffusion or flow model fixes its state at the very start, a fixed number of pixels or a fixed sequence length. Every step after that just refines the same fixed size vector. The shape of the output is frozen before the model has generated anything. That clashes with how a lot of real data works, where the size is part of what you want to model. Images and shapes come at any resolution. Audio and video run for any duration. Language has unknown length. To handle these, the state space needs to be able to grow during inference, instead of being committed to upfront. The tool they build on is the flow map. Standard generation follows a smooth path from noise to data, but integrating it needs many small steps. A flow map learns to jump. Given the state at time s, it directly predicts the state at a later time t, using an average velocity over that interval. That's how you get 1 or 2-step generation. Now the key move. They factor that jump into 2 learnable pieces. First, an expand operator inserts brand new coordinates or tokens into the state, conditioned on what's already there. Second, a transport map pushes the enlarged state forward and denoises it. Compose them, and a single map both grows and cleans up the state at once. And here's the elegant part. If the expand operator does nothing, if it's the identity, you get back exactly a standard fixed-size flow map. So this isn't a competing method, it's a strict generalization. Fixed canvas generation is just the special case where the canvas never grows. Let's make it precise, starting from the standard picture. A stochastic interpolant draws a straight path between a noise sample and a data sample. The model learns a velocity field, which is just the expected direction of travel at each point along that path. Notice the hidden assumption. Every state along that path lives in the same fixed dimension. The velocity field is a map from that space to itself. There is simply no room in this formulation for the state to get bigger. So they generalize it. Replace the fixed dimension with a dimension schedule, a non-decreasing function that says how big the state is at each time. Now the path runs between distributions of increasing dimensionality. The state space itself grows as time moves forward. This immediately creates a problem. If an earlier state is smaller than a later one, they live in different-sized spaces. There's no smooth invertible map between them, and no ordinary velocity field can carry one to the other. You can't denoise your way from a small state to a bigger one. The fix is the expand operator. To bridge the size gap, it takes the current state and appends fresh coordinates of noise, drawn from a simple distribution, lifting the state up to the target dimension. Only once both live in the same space can a normal velocity field take over. Where those new coordinates go is a design choice, and it's flexible. You can concatenate them at the end, which is natural for autoregressive sequences or point clouds. You can interleave them at chosen positions, which suits any length text or infilling. Or you can attach each new coordinate to a parent, which is perfect for course-defined structure. There's a subtlety. Coordinates are born at different moments, so they are at different stages of denoising. The trick is to give each new coordinate its own local clock that resets to 0 when it's inserted and runs to 1 at the end. Every dimension is then denoised on a common, rescaled schedule. Put the 2 pieces together, and you get the expanding flow map. Expand the state to lift it up, then take a flow map step with the average velocity in that enlarged space. One learned map that simultaneously inserts new content and denoises everything toward the target. Now, expanding and transporting are 2 different kinds of motion, so how are they one process? The answer is a piecewise-deterministic Markov process. Between insertions, the state drifts smoothly under the velocity field. At random moments, it jumps to a higher dimension. A single generator, drift plus jumps, describes the whole thing rigorously. This framework really shines on discrete data, like text and molecular graphs. Here the expand operator becomes token insertion, and the transport map becomes token denoising. Sequence literally grows from a single token into a full sentence, inserting and cleaning up as it goes. The crucial new component is the insertion head. Between any 2 active tokens, there's a gap, and the model learns to predict how many new tokens belong in each gap over the next jump. It's trained with a simple count-matching loss, so it learns the expected number of insertions directly from data. How you sample those counts turns out to matter a lot. They draw each gap's count from a binomial against the remaining token budget. For many small steps, this reduces to the familiar Poisson jump. But for a single big jump, generating the whole sequence at once, the Poisson blows up with huge variance while the binomial concentrates on the exact count. The discrete expanding flow map mirrors the continuous one exactly. Insert the new latent tokens with the expand operator, then denoise every token toward its final one-hot value with a mean denoiser on the simplex. One step that jointly grows and cleans a discrete sequence. So how is this actually trained? You train one network to do both jobs. The velocity, or denoiser, is supervised along the diagonal, where the flow map reduces to the ordinary instantaneous velocity. Inconsistency losses tie together different time pairs, so long jumps agree with short ones. In discrete land, you add the insertion loss for the counts. And sampling is the whole point. It's cheap. Start from almost nothing, a tiny state or a single token. Then, for however many steps you can afford, expand and denoise. Because the same network handles any jump size, you dial the step count from 100 down to 1 with no retraining. Payoff is one recipe that spans everything. The very same construction handles continuous coordinates and discrete tokens, smooth transport and discrete insertions, many-step teachers and one-step students. Let's see what it does in practice. First, generating 3D molecular conformers. Here the expand operator grows a molecule coarse-to-fine. Denoise the heavy atom skeleton, then insert the hydrogens around it. With just 20 steps, their model matches or beats diffusion baselines that use 500 to 1,000 steps, and distills all the way down to 1 to 4 steps. Next, discrete molecular graphs, where the model grows a graph from empty by predicting how many nodes to add. As you cut the step budget, the strong baseline collapses down to 54% valid molecules at 4 steps, while their model stays above 90%. At a single step, its distribution score is nearly 5 times better than the prior few-step method. And finally, variable length language modeling on the 1 billion word benchmark. Growing the sentence token by token, their model beats a strong fixed-length flow map baseline at every sampling budget. And in the aggressive 1, 2, and 4-step regime, it improves on prior methods by very large margins. So here's the whole idea in one breath. Split generation into growing the canvas and denoising it, tie the two into a single flow map, and you can generate continuous or discrete data whose size is decided on the fly, in as little as 1 step. Output size stops being a setting you fix and becomes something the model learns. If that was satisfying, subscribe for more papers decoded in full.